Honorable Speaker Dr. G.C.Nandi, dear participants and faculty members of FCRIT Vashi, a very warm and heartfelt welcome to one and all. I am Ruben Pereira.
I am Omkar Parkar, and it's our pleasure to host this seminar on behalf of FCRIT MESA. MESA is pleased to bring you MESH 2021.
MESA stands for Mechanical Engineering Students Association. We host a number of events throughout the year, including Synergy, MESH, and Caliber, along with various technical and non-technical workshops. These events are possible due to the contribution of brilliant minds and dedication displayed by our MESA committee under the leadership of staff coordinators and our head of department.
As the name suggests, MESH is an interlaced structure, the interlacing of knowledge and exposure to current trends. It integrates academic knowledge and technical knowledge. Today, we have an eminent speaker from IIIT Allahabad to share their immense knowledge, which would help us all for our future endeavors.
Dr. Deshmukh is the head of Mechanical Engineering Department and Dean Faculty at Admiral Charities, Father C. Rodriguez Institute of Technology, Vashi. Dr. Deshmukh has completed his PhD from IIT Bombay and has been actively involved in various aspects of academia and research for 22 years. I request Dr. Deshmukh sir to kindly address the attendees.
Yeah, I'm audible?
Yes, sir.
Yes, sir. Yeah. Good morning, one and all. Dr. G.C.Nandi, Professor and Head of Center of Intelligent Robotics, IIIT Allahabad. Dr. Kavi Arya, Professor, Computer Engineering Department, IIT Bombay. Faculty members and my dear students. Here, I welcome you all for today's event, that is a MESH. And every year we're organizing this MESH, and we used to call the professor from IIT Bombay. And due to this COVID pandemic, we got, again I can say, we got an opportunity to interact with the people from apart from the Mumbai. And so we took this opportunity and we tried to contact Professor Nandi and Professor Arya, and they accepted our invitations. We are very much thankful to them. And as you know, that mechanical engineering is a very wide scope. There are a variety of fields where, as a mechanical engineer, students can work in the future and they will have the bright career. But we should have certain skill set, then only we can grab that opportunity. And for getting that one, such kind of the events will be very much useful. And I'm sure that today's sessions, the students will be very much, today's sessions will be very interactive, and students will interact with the today's two speakers, well-known speaker in a particular field of robotics. And I hope the event will be more successful, and I wish all the best for today's event. Thank you.
Thank you, sir, for encouraging us. Your words will act as concrete foundations on which we build ourselves.
Now we'll begin with the technical presentation. We have Dr. G.C.Nandi. Professor G.C.Nandi currently works as the professor and advisor of the premier Indian Institute of Information Technology, Allahabad. His area of interest and specialization is artificial intelligence and robotics. He regularly teaches subjects like machine learning, deep learning, and robotics at IIIT Allahabad. He has developed a robotics and artificial intelligence laboratory, which is considered to be the best in our country. He and his team have recently developed a technology called Adaptive Modular Active Leg, which is an artificial limb which can give maximum comfort to an amputee with minimum cost. He works with his team of undergraduate students, master's students, PhD scholars in the area of machine learning, with special focus on deep learning and application in collaborative robotics, particularly in the area of multimodal human-robot interactions and intelligent robot grasping. Some of his many achievements are National Scholarship by Ministry of Human Resource Development, Government of India, Doctoral Fellowship by External Scholarship Division, Postdoctoral Fellowship awarded by the Chuck, Hong Kong, Indo-Swiss Joint Research Award, Visiting Professorship Award by EPFL University of Switzerland, and many more. Now I request Sir to take over and proceed with his seminar on robotics, kinematics, and control.
Okay, good morning, dear, and welcome to all to my lecture. So I believe I am audible, right?
Yes, sir.
Yes, sir.
Okay, now let me share my screen. Okay. Okay. So, okay. Is my screen visible?
Yes, sir, it's visible.
Okay. So it is written robot kinematics and control. Okay, so that's very close to my heart, but in that field, I worked long back. I am a mechanical engineer, but as you introduced, by training. But from 1986 onwards, to be frank enough, forgot design, strength of material, many aspects of them. Okay, because I slowly migrated to another very exciting field. I taught several subjects because this institute, from the very beginning, I was associated with programming, then the operating system, then algorithm, all the hardcore subjects of computer science I taught. And in that process, I learned with many of my very smart students who are settled in our country or abroad at various prestigious institutions and organizations. So today I am going to introduce, because mechanical engineering domain, as your HOD was telling, is having many facets. And today you need to understand the rapid changes which is happening. I still remember my first campus placement job was in an automobile industry. That was one of the very premier automobile industry in India. Which is considered to be mechanical engineers' heaven, because you can see the entire mechanical engineering in an automobile industry. So there, and we are very proud that this car, that is a product which we have, and mechanical engineers have many products. Okay, they are hardcore mechanical engineering. But the situations are changing. You see, Elon Musk, the name is very famous. And recently, I was, while I was in the US, I was seeing, and actually I was riding a car, Tesla, which has completely revolutionized the field. As a mechanical engineering student by training and then faculty, initially it was very shocking for me to see that engine is not there. The transmission as such is not there. There is no gear. Okay, there is one gear, but there is no transmission. The heart of car. So they are slowly disappearing. Okay, so the car is dominated by computer. One computer is actually controlling the car, and there are motors, and it is electrical car. So I'm telling you all this because you need to understand that rapid changes taking place in mechanical engineering, and you are to be ready to accept those challenges. Okay, so hardcore mechanical, which we earlier used to think, many things will change. They will not be there. The car is completely different, except the body. Very few mechanical things are there. Design, of course, has to be there. So robotics is one such field which actually is a multidisciplinary in nature. Okay. So let me just start. By the way, is this the first class in robotics, or you have some? You have some. I understand you have some courses already in robotics, so you understand that what robot is. A robot is a reprogrammable universal machine. Reprogrammable universal machine. So first time, this is a reprogrammable machine. Means you can change the program and the robot will act in a different way. So that's why universal machine. So it is not the single spindle automat, multi-spindle automat type of machine, which can do tremendous job with high production capability, but they are dedicated for a particular product. So CNC machine robots, they are a, a different kind of machines which are reprogrammable. Means computer is an integral part of those machines. Okay, and the robot has to be also another specification that this is not enough. Reprogrammability, yes. Universalness, yes. But another, it has to have 5 degrees of freedom if it is a manipulating type of robot which is trying to imitate our hand, or it has to have 3 degrees of freedom if it is a mobile type of robot, field type of robot. Why these constraints are coming? There is an interesting story. When robotics field was new in 1960s, there was tremendous growth in this field, and lot of it landed on the ground from science fiction, and the term robot were used by everybody, every country. It was kind of prestige issue that how many robots a country is using or producing. So one country, Japan, who is very advanced in this area, they used to display on their Narita airport that we are the nation using so many robots. Actually, they were calling everything as robot. Whatever is a programmable machine is robot. Okay, but not all programmable machines are robot. That's why in 1977, IRIS, that is the International Forum for Industrial Robots, they decided that we'll have to check this train, and they put this constraint, 5 degrees of freedom. I understand, you know, degrees of freedom. What is degrees of freedom? Degrees of freedom is actually a system's address. If a system is represented by n number of independent coordinates, then its degrees of freedom will be n. So here, robot is actually a open kinematic chain. Manipulating robot is open kinematic chain, and it has to have 5 degrees of freedom, excluding gripper. So that's the definition. And as I told you, it's a multidisciplinary area. So I have some cool videos. Let me see whether, due to bandwidth, whether they are playing or not. If they are not playing, then I will not play them, try to play them. But if they are playing, then I will use them. So this is my, by the way, this is my new videos which we have uploaded. It talks about intelligent grasping by a cobot. What cobot is, I will also tell you.
Nandi sir,
Yes.
does this video have the sound?
Yes.
Actually, we
The
are
sound is not there?
sound is not there. While actually sharing the screen, no sir. We have to check
Okay,
a
okay,
box
okay.
include systems audio. I guess you can
Okay.
explain.
Okay, okay. Okay. No problem. So, but the video was visible, right? So
Yes,
sound
yes, video
was
visible.
not.
Yes,
So
yes.
that is there in YouTube. So by the way, I have a channel. If you type, I am telling the students, say G.C.Nandi, then you can see video lectures, which I am developing. At least 8 of them are in robotics. So you will get a clear understanding from ABC, the how robot works, what are the challenges and all kind of thing. So that's not an issue. And there are also some 45 video lectures on machine learning and deep learning I am preparing. So this for my students, you can just subscribe the channel and you can enjoy seeing all the developments. So you can see the term robot actually came from Slavian language. Slavian language means, you see, Czech, Russian, Bulgarian, they have a different kind of language. The origin of the language is Greek, whereas all other languages like English, German, French, their origin is Latin. So, there the term robotat means to work. Okay, so it's very surprising if somebody lands in Moscow, you will see a lot of people are talking about Devi Robotics, means robot are everywhere, means they ask where do you work, what is your work about. So Robotat means to work. So the Isaac Asimov, perhaps you know that the guy who migrated from Russia to US and wrote science fiction and first used the term robot. No wonder, because he know that what robot means. There's something which will try to comfort human in replacing the hard, laborious and repetitive job. Then robotics society, then there are so many societies grew over the years, and Robotics Society of America, they actually gave this kind of definition, which I told. It's a reprogrammable, multifunctional manipulator for design to move material, this. And for moving, you require degrees of freedom. That's why 5 degrees of freedom it requires. And when we actually design robot, behind our mind, we try to imitate, very vaguely though, but we try to imitate human. Okay, so what we have morphologically, you see, we have a central nervous system, which is brain. Okay, and this is, by the way, what are these? These are actually a huge network of neuron, the basic computing element in our body. And how many are they? They are 100 billions. And in number, when a child is born, it's gifted by the nature with those many neurons, and 1 trillion interconnection is there. So it's a gigantic network, which again, vaguely in this era of cloud computing, we are trying to imitate. So as you know that unlike body cell, these neurons, they do not multiply. So over the years only they get decades, but nevertheless they are the computing element which compute. Okay, am I audible, right? Am I audible?
Yes, sir.
Yes, sir. Yes, sir.
Okay,
Okay.
Yes.
Okay. So these are the computing element, but the computation in human is different than the computation which is taking place in case of robot, because today we have only digital machine. Okay, although a lot of serious research is going on that how can we compute the way we compute. We never compute digitally. Digit is very much alien to us. That's why a kid need to learn digit 1, 2, 3, 4, all this. Okay, and even at any age, we are very poor in manipulating the digit. You can see, doing a small experiment, whenever OTP comes for a few seconds, right? Everybody, at least I do, I try to memorize a pattern which is hidden in the digit, and that too in my native language, so that if it disappears, I will remember it and I will punch it. Another experiment you can do, if you have a mobile number, you are sharing it with somebody, it's very difficult for you to spell that big mobile number at a stretch. Unknowingly, you have created some kind of pattern out of it so that you can memorize it. That I have seen even true for the security guard. When I ask what is the phone number of some person X, they tell 25 28 because for him or her it is very difficult to remember that whole number, but it is very easy to remember the pattern, which is consists of two numbers. Anyway, by the way, so this is this shows that we are very good. While we are very good in pattern manipulation, we are very poor in big digit manipulation. But since we have today digital machine, okay, so we'll have to have a computer which understand the way we command, the way robot should move. You see, this is vaguely inspired by human. So a robot has also a computer which is analogous to our brain, and apart from that, robot has to have another computer, because we have central nervous system, we have spinal cord. Here also a lot of computation is going on. Okay, so and mostly those computations are reactive in nature. Say you are learning bicycling, or your first kid is trying to walk, which is extremely difficult because our body is an inverted pendulum like structure. So one need to understand how to balance that, and during understanding, brain is involved. But after that, you see, you can walk very easily because your control is taking care of the spinal cord, which is a lower level of information processing center, or rather execution level information processing center, and it takes care of rudimentary, repetitive kind of action, so that our brain is free to do the high level job of thinking this, that. So here all the thinking and planning level job is done on this machine, which is computer. And then we have links, okay, and this computer cannot do anything in moving, right? So we'll have to have at every joint level, we'll have to have a dedicated processor, okay? So that, and another computer which is analogous to our peripheral nervous system, that is the spinal cord, another computer system which is dedicated for moving the joints or following the commands which is being issued by this computer. So we'll talk about that. Every computer, every robot has this architecture. It cannot be anything else, okay? There has to have a computer where planning level activities have to take place. There has to have a controller dedicated for commanding, that will sit in between this computer planner and the executor, and that will ensure that whatever planner is telling, the execution has to be done perfectly, okay? And you can see robot is actually moving. So this is a Puma robot. I have put it first because this is the first industrial robot in the world which appeared by Dowell company in 1960s. They actually got the patent, and that's the beginning. Then KUKA is modern industrial robot. They are trying to imitate human hand, okay? So Puma can be configured as human right hand. Puma can be configured as human left hand. So perfectly, which we try to imitate, at least from kinematics point of view, seeing what are the advantages we have, we try to imitate those advantageous things here. One of them, as you know, if you see a Puma robot, by the way, have you seen Puma robot? Programmable universal machine for assembly. It's known as Puma. It is the grammar of robot, you can call. Anyway, this gripper, there is how many degrees of freedom it has to have? 6 degrees of freedom. And you see, what are those 6 degrees of freedom? I will just elaborate. 1 degree of freedom about this axis. This is shoulder another degrees of freedom about shoulder, this is elbow, and 3 are here embedded on the wrist. The reason, perhaps you know, in the class you are taught that Piper, there is a graduate student, okay, he actually during his PhD thesis, he told that if 3 joint axes, if joint axes of 3 joints are intersecting at a point, then closed form kinematic, inverse kinematic solutions are guaranteed. Although I do not believe we are doing inverse kinematics, but if you can see, we have 3 degrees of freedom embedded on our wrist. What are those? One is yaw, roll, and pitch. I'm sorry I could not show with my wrist, but I think it is known to you. Human has 3 intersecting joint axes, and although we may not solve the inverse kinematics, but since he proved and that inverse kinematic solution will be guaranteed, everybody is actually imitating. No company, no industry wants to take venture, so they are following Piper's recommendation. Although that recommendations are sufficient condition, not necessary, but this is a fact. KUKA also has similar kind of morphological structure. There are so many different kinds of robots. Few I have shown here. These are the humanoid robot. Okay, so when I talk about kinematics and control, they are to some extent robot specific. But that's why I will try to make it as generic as possible so that you can understand every robots available in the world, how they actually move, following those principles. Okay, these are now robot. Again, we have now robots. We are extensively working on human-robot interaction on this kind of robot. Again, in my video channel, you will find several such recent research we are doing. Means we are communicating with the robot using our gesture and speech, because the next era is going to be the era of language. Means all the scientists around, computer scientists especially around the world, is trying to make computer to learn the language, the way we learn, not the way so far we are solving speech recognition problem. Okay, that's another forum we can discuss. But there are different kinds of robots I wanted to show you, and they are all human inspired. Okay, so these are all imaginative robots which actually came into existence. Okay, so you see, to qualify, and just like human, you see what we have is processing system. We have. Apart from that, what we have muscle, which are actuators. Actuator means we have links. First of all, we have links in the form of limbs which you cannot see. Skeleton you can see. Okay, and those skeletons, those bones, they are connected with the joints and forming a kind of open kinematic chain for hand. Those are called links in robot language. And then we have muscles, that is actuator, which are causing those links to move. A skeleton cannot move, but a human can, because we have actuator. So in robot also we have actuator, different kind of actuator. Most common is actually electrical, motor. Other actuators are also there, pneumatic, hydraulic, depending on the load carrying capacity of the robot. But the most common one is electrical kind of actuator, because they are comparatively easy to control. And then what we have sensors. So robot ought to have sensors. We have different kinds of sensors, enriched with several sensors, right? And the robot has both internal sensor and external sensor, like the way we have. Okay, so, and sense create perception for us. How? By processing sensory information by the computer, right? And for our case, it is learning based. Okay, okay, and it can carry out different tasks like locomotion, manipulation. A kid, when he or she is trying to stand on his feet, lots of sensing, acting is taking place to balance the inverted pendulum-like structure. Okay. So these are different kinds of robots which we have, and we have in our laboratory in digital space some 450 different industrial robots. But their kinematics are similar, principles are similar, which we are going to talk. These are another kind of robot. You see, this is drone now, flying everywhere, and these are wheel mobile robot, these are underwater robot, they are leg robot. From kinematic principle point of view, they are, although similar, they are very different. They are very different. Leg locomotion kinematics are different than wheel mobile kinematics. Okay, than our manipulating robots kinematics. But most complicated, most complete kinematics is manipulator kinematics, which we are going to talk today. So these are some of the examples of a robot. Now, how robot function actually? That there is a, you know, that there is a computer, but computer cannot do anything except passing order and giving data. Okay, and that too to another computer, it can share the data, right? So how robot function? Very good. So let us discuss how robot function. And here is the role of kinematics and control is there. So you see, this is an example of two-link robot manipulator. So by any definition, this is not robot, because having two-link does not qualify it to be called as a robot. But for demonstration purpose, for writing purpose, for writing the principle, we can use this. Is a planar two-link manipulator on Cartesian space. So what you can write that any point on the Cartesian space, say x, y, so this is x, y, this is the location where I am my robot hand. It could be a gripper kind of thing here. A robot hand is there, okay? So by using your simple trigonometry, you can just write down the relation between theta and x. What is x? X is, so this is the linked length of the robot, L1, L2. Say at any instant of time, it has made an angle theta 1 with x-axis, and this link has made an angle theta 2 with the first link. So that means this angle is theta 1 plus theta 2. Theta 2 actually is defined an angle which is second link is making with first link. So then you are very comfortably can write this simple relation which connects Cartesian space to the joint space. X equals to L1 cos theta 1, L1 cos theta 1 plus L2 cos theta 1 plus theta 2. Okay, so this is X, isn't it? So this plus this. And what is Y? Similarly, Y is L1 sin theta 1 plus L2 sin theta 1 plus theta 2. So everybody with me, right? So you understand, you have seen this two tiny equation, but they are telling tremendous, tremendous information is hidden over there. You see, if, so how the joints will be moved? Joints will be moved by some actuators. Say there are motors, okay? Although motors are not kept in an actual robot at the joint because they are heavy, there is some transmission device, they are kept at some convenient places. But let us assume that there is some torque producing mechanism which is actuators, they are here, they are moving, they are making the link to move. So if I move this motor and this motor, then the link will move, okay? And see, whimsically, if I move theta 1 and theta 2, which are the function of time, then as a result of that, I will get my end effector to reach some x and y unambiguously. There is no doubt about it, right? So it cannot have any other place than xy. So that's called forward kinematics. So by the way, you have two space now. One is Cartesian space, and another is joint space. So we can call it theta space. This is x space. So if this is given, joint space is given, and you are computing Cartesian space, they are called forward kinematics, okay? Forward kinematics. How about that? If I specify Cartesian space and try to know what is my joint space. That's a problematic. Why problematic? You can look here. Why it is problematic? You see, when this xy is given, you have multiple solutions. There is no unique theta 1 and theta 2 which can make the end effector reach here. Say, for example, you can draw another parallelogram. Okay. So this is another solution. Okay. Another solution, potential solution. Okay. So this theta 1, another solution. And this is problematic even for planar two-link manipulator, which is not qualified to be a robot. Why the problem is there? You can ask yourself, because if the left-hand side is known, this cosine is a series, this sine is a series. So you have lots of theta 1 square, theta 2 square, and as many terms you will take, that many solutions you will get. It will be quadratic equation. You will have to solve a quadratic equation, cubic equation. And look to your own hand. You see, my hand is a perfect example of 3D robot manipulator. Okay. And suppose some mosquito is biting on your nose tip, and your hand wants to go there, reach there. So what will happen? There are innumerable ways. You can just experiment. Manipulating your shoulder, elbow, and wrist joint, there are innumerable ways your hand can reach to the nose tip. But look, from our childhood, we have solved the optimum problem, right? Our hand will follow reactively the latest, the smallest path. So unknowingly, we are solving an optimization problem. But robot will not be able to do anything if we do not plan properly. So we'll have to solve inverse, and by the way, this is called inverse kinematics. Inverse kinematics. So when your Cartesian space is given, your planner is trying to synthesize joint space, it is called inverse kinematics. Okay, and depending on the manipulator to manipulator, if it is a real robot like this, then yes, it is problematic, because there will be multiple solutions, as the theory is telling you, because they are transcendental equations, sine cosine terms are there, and they are series, and so multiple solutions will be there. Okay, and you have to devise something that out of multiple solution, a robot should be able to pick the optimal solution, for which from its current position, the movement of the joint should be minimum. Why? Because movement of the joint requires energy to be spent. So that's why we can, we actually following the optimal way in moving our hand from anywhere to nose tip. We are not encircling our heads and everything in our working envelope to manipulate our hand. So optimization is required here. And by the way, this robot, this is not a robot, but this manipulator has a working envelope which can also be designed by from seeing these two equations. You see, if you run two loops, say theta 1 and theta 2 is my inner loop, okay, and suppose you give each theta angle has some say minus 45 hypothetical to plus 45. Every joint will have some range, including our hand also has some range. We cannot reach everywhere. You cannot reach your back some points, right? Those are, by the way, are not reachable, and those are called working envelope. Working envelope is a space where robot can move, and how to design the space is not easy, but it's easy to visualize. If for two-link robot manipulator, I simply need to run two for loop, okay, and collect the data and fit a surface kind of thing if it is plane. And here it will be two circle, okay, like this. If you run and collect the information, this is the working L1 plus L2, and this is L1 minus L2, okay, kind of thing you will get. So this tiny equation will give you everything. Inverse kinematics, how to solve inverse kinematics. How to solve inverse kinematics then? You see, there are ways to solve it. You can use your class 12 knowledge and then eliminate theta 1 and theta 2 and can get some values in terms of x, y, L1, L2. But that's not sufficient because we are talking about real robot, which is a special mechanism, right? Having 6 degrees of freedom. So this, although is good for understanding, but it's not enough for analyzing those kind of structure. So for that, we follow certain rules, which I am going to tell you, that special kinematics. Okay. So this kind of thing you have already seen, right? So Deshmukh way back 1955 told that how to establish kinematic relation. So what kinematics is, by the way, you now know. There are kinematics is the geometrical relation between Cartesian space and joint space. Okay, and without considering mass, etc., etc. So that's a simple model, right? So everybody needs to create fast model of a robot. Why we need to create model? Because otherwise I cannot program it. I cannot make my computer understand a physical structure. Computer doesn't understand any physical thing, right? It understands matrix. It understands some function which is written in the form of code. So I will have. That's the reason I will have to model, and it understand, very well matrix. Okay, so if I represent my structure in the form of matrix, then computer will understand, and we can do many things. We can solve forward kinematics, inverse kinematics. We can plan trajectory. We can create Jacobian. Okay, so that I can actually move my robot. So all kinematics control. Why do you study? Because computer will give command, but somebody has to move, right? Without kinematics and control, the physical structure will not move. Okay, so this is a very systematic way, Deshmukh principle, which gives you the notation, the relation between two adjacent link, any two adjacent link. Suppose and they have a kind of rules. Say this is my one link. Okay, this is another link I minus 1, link I, and all the joints are actually revolute joints. So this is a joint. So this joint is holding link I minus 1 and link I. And this is an example where joints are having prismatic joint. This is revolute joint because only it can move in circular way. Here in a translatory way it can move. So this is called prismatic joint robot. Okay, it can move up and down. But the DH principle is similar to both. So what is the principle? He told that using maximum only 4 parameters, I can establish kinematic relation between two adjacent link. Okay, so if this is my one link, and then the moment you get link, you see where the motion has been created. So this link design mechanical engineer will do, and they will give it to you. Okay, and as a computer engineer, you will have to design the planar. Okay, and mechanical engineer also can do the planar, but I am just telling. And for designing planar, you need to know all these things. Okay, so first you have to know that whenever there is a motion, we assign the axis z axis. Okay, here the motion can take place about this. Okay, because it is supposed to hold through joint another link. It's chain. Okay, so this is another joint axis Z1, Zi. So this is the ith axis. Link I can be actually this is assumption. What is that assumption? Each link in the robot is a perfect rigid body. If that assumption is not there, then the analysis will be much more difficult. But in case of and that assumption is quite logical. Okay, that each link is completely perfect body. Of course, when they are joined, it is a chain. It is no more a perfect rigid body, but each individual link is a perfect rigid body. That assumption is there. And what is the definition of rigid body? You know, you can assign coordinate frame, body coordinate frame anywhere, and any points on the link actually will have a unique position vector with respect to that body. If that is the case, then it is a rigid body. Okay. So simply, if some load is there and that this position vector changes, then it is not a rigid body, which obviously will happen. Some amount of deflection will be there, but we'll ignore that. If you do not ignore, then you will have to do finite element analysis, which will give additional complexity in the robotics, which we do not want. Okay. So that assumption is there, that individual links are perfectly rigid body. So here, we have assigned coordinate first. If the links are given, you will have to assign coordinate frame. So you assign z-axis wherever you can find the motion. So motion is about this, about this, about this. So place all the z-axis, zi minus 1, zi, zi plus 1, so on and so forth. Here also, you see, there will be up and down motion due to this prismatic joint. So your z-axis will be along this. Okay, this is revolute joint. If something, this link is connected with a revolute kind of link. Okay, so this could be your. So you will have to assign coordinate from z. So z is done. Okay, about z you will measure the motion parameter. Now, what is the distance between two successive joint axes? Okay, so the distance is defined as the common normal between the two axes, because common normal, as long as this is rigid body, will perfectly give you the notion of the length of the link. We are not interested to know the physical length of the link. Why? Because it's a perfect rigid body. If once I can know the common normal, I can calculate any position, any point on this rigid body perfectly with as long as the position vector doesn't change. So that's why actual physical length, link length, has very little relevance in my. Only they will add complexity. So I want to notionally calculate the link length. So how to calculate the link length? According to DH principle, the link length is the distance of the common normal, okay, between two successive axes. So zi minus 1, and you assign x-axis in the direction of the common normal. So this is my xi, zi I have assigned, this is xi. So xi is the common normal between two, this is special link, you can understand. So this is the minimum distance. Now immediately one can raise question that if the two axes are parallel, then what is going to happen? Yes, this common normal will no more be unique. There will be infinitely a large number of common normal, they are equal. Okay, so these two are parallel. When they are two are parallel, anywhere you can assign xi as per your convenience to make that origin of the coordinate frame. So I need a coordinate frame, by the way, okay, to actually define any rigid body. Okay, so what I need coordinate frame which is known as body coordinate frame. Okay, and any points description is known with respect to this body coordinate frame, and when they are connected to some other link, so I need to also capture the orientation of this rigid body can be captured by, I am skipping actually this because these are too fundamental, I believe, for you, by 3 by 3. Is it fundamental or not? Then we can go to that depth also, that any rigid body's orientation can be captured by 3 by 3 matrix. Okay, and as you know, so is it known to your student who have undergone robotics course or graphics course? Because by my my understanding is this is I can skip. That's why I have came. Hello.
No, sir. Fundamental. Start from the basic. That will be fine, sir.
Okay, so these are known, right? What is rotation matrix? Rotation matrix actually gives the orientation when actually this is about, say, about this axis. This is making a motion, right? So how to capture the position like as a this like this. So this position vector has gone here. So how to describe the new position of the orientation is actually given by the rotation matrix, which is 3 by 3 matrix. We can deduce it. Okay, but also to understand kinematic relation or describe kinematic relation, we need to have a fixed coordinate frame. Otherwise, we cannot describe these rigid bodies. Translation orientation is fine, but translation you need another coordinate frame, which we call inertial coordinate frame, which is not supposed to move. Inertial coordinate frame. Okay, so using this inertial coordinate frame, then our matrix structure, it can be shown actually that it has beautiful property. In graphics, you have learned that R is orthogonal transformation, orthogonal matrix, and then R transpose equal to R inverse. Okay. And in robotics, we need to calculate matrix inversion always. There are tons of matrices, inversion of which has to be calculated. And as you know, calculating matrix inversion is not easy. It's complexity, computational complexity, that is big O, is n cube, which is very, very bad. N is the number of elements in the matrix. So it is really very bad. So we need always that we will calculate inversion, but I will exploit this structure. So for as long as it is only rotation matrix, you don't need to calculate inversion. You just calculate transpose, because this is orthogonal transformation. R transpose equals to unitary matrix. So R transpose equal to R inverse. Okay, so you don't need to calculate the mathematical inversion. Now, as I told you, when additional coordinate frame, inertial coordinate frame is there, because it is required to capture the translation of the rigid link, then I will have to create a column and augment it here. So what is this is my 3 by 3 matrix. I have augmented Px, Py, Pz, which is the coordinate of the origin of the body coordinate frame with respect to inertial coordinate frame. Okay, this now what happened? The moment you do, earlier it was 3 cross 3. Now it is 3 cross 4. 3 rows. Okay, 4 rows and 3 column. 3 cross 4. Okay, and it loses its property, orthogonal property. So what we do, we homogenize this matrix by adding additional row that is called homogeneous coordinate transformation matrix. You know, that is R, and then you have P and 0, 1. And structurally it is again 4 cross 4. But this also doesn't have the property which R has. That is this transpose is equals to not is inverse. So we need to, there is this little theory. I will skip that. These are all known, I believe. Otherwise, you can read Craig's authentic book. We have there, J.J. Craig. Okay, beautifully it has explained to you. Here I am trying to give you a notion that once you know the transformation matrix, how to invert without mathematical inversion, then most of the problem is solved. And here we are trying to express using DH notation the links description with the help of a transformation matrix T 4 cross 4 homogeneous coordinate transformation matrix. And what are the elements in that matrix? One is theta, which is motion parameter. Another one is link length. Okay, and you see then this is angle called twist angle, which is measured about this x-axis. Okay, which tells you if you can consider a plane passing through the with this, okay, and you can project this axis there, and the twist angle alpha I minus 1 is the angle between Zi and Zi minus 1. So this is another DH parameter, which is twist angle, which is called twist angle. So twist angle, common normal, motion angle, theta, right? So another DH parameter is the distance between two successive common normal. So this is a common normal which is capturing the link length I minus 1, and it is measured between I and I minus 1. This is another common normal xi, which is capturing the motion notion of this link measured between I plus 1 and I axis. So the distance between these two common normal, okay, is called di, the distance between two common normal. So with the help of this 4 parameter, DH principle tells that you can completely kinematically describe one link position and orientation with respect to other link. And that means I can, you see, this is a very important thing. So any link I minus 1 can be captured with the help of 4x4 transformation matrix. So how it came? It came, so once you have assigned coordinate origin, okay, this, if there is another link, that also, everything you will have to do. So here you can argue that so this is only 2 axes, x and z. Where is y? Y is there, but we need not write them because this is following orthogonal coordinate system. The moment x and z are defined, y cannot go anywhere. So y is there, but we can ignore it because otherwise this figure could be clumsy and they are not donating anything, no new information. Okay, so now you see, having defined those 4 parameters, we can completely describe, say, I minus. So this and this completely should be overlapped. How to overlap them? First, I can rotate about this axis by an angle theta. Then I can translate about z axis about by an amount di. So this origin from here, it has reached here. So then I can translate that origin here by translating it along x-axis by an amount this, and then this twist angle is there. So I can give another rotation about x-axis so that completely I axis and I minus 1 axis will be completely overlapping. Okay, and this is the resultant matrix called Mother matrix. So a mechanical engineer, when a design is giving, first job is to do the DH table. This is very important. If you make any mistake, then your robot, you cannot plan, you cannot make it reprogrammable. So DH parameter, DH table. So the moment designer has given you the robot, the link length, twist, etc., will be known to you, and you will have to figure out the DH table. Once DH table is there, and then you have this matrix, okay, Mother matrix. So repeatedly, you will have to put all the DH parameter. You read one row and put sine theta, cos theta, alpha, this alpha, di. These are actually, theta is actually DH parameter, alpha I minus 1 DH parameter, AI minus 1 is a common normal. Then that is another DH parameter, di another DH parameter. So with those DH parameter, you can calculate just corresponding to this row, you can design. So I equal to 1 with respect to 0, 4x4 matrix you will get. Then you read another row and you give birth to another matrix. Okay, you read another row and use the same Mother matrix and create. Okay, so in this way the process will continue and you can have the complete model of the robot. Okay, so one good thing about industrial robot is one joint has only 1 degree of freedom, unlike human hand. Okay, so that's the good thing about it. So step 1, robot is given to you, you prepare DH table, and then from DH table you calculate all the individual matrices, and then you concatenate them, say for Puma. And they are the function of only one parameter. Because structurally, if you see DH parameters, out of 4 DH parameters, only one is variable, others are constant. The moment somebody has designed the robot, its length cannot change, its twist angle cannot change, its DI cannot change. Only change can take place if it is a revolute joint, theta will only vary. If it is prismatic joint, DI will only vary. So that's a good thing, because we do not want unnecessary complexity in moving the robot. That's why every joint has 1 degree of freedom only. And then, of course, if this is given in the form of a 4x4 matrix, then you are asked to solve all the theta I equals to 1, 2, up to 6. Then it is called inverse kinematic solution. Okay, which is not so easy. It depends on robot to robot, but for Puma, we know what will be the inverse kinematic solution. For Bester robot, we already know what will be the inverse kinematic solution. So inverse kinematic solution is a very realistic one, because you see in our tiny robot, which we have shown you earlier here, it is very common that we will command robot to follow a trajectory or go some places in the Cartesian space, right? We are not playing robot with some theta, theta 2, right? This is called simulation. But for any action, we will give the Cartesian space value. And the moment you are doing the Cartesian space value, normally robot needs to draw a trajectory. So how to draw the trajectory? The fundamental raw materials is this, to solve inverse kinematics for any robot. And that's not easy, but I told you how to do that. And in that solution, we will never accept. Please remember, many books have many inaccuracies in this regard. All theta i's, I will accept theta I in the form of a tan 2 function only. Okay, comma. What does it mean? This is simple tan inverse function is not acceptable in robotics. Okay, perhaps you know, that's why I did not mention it, but very interesting. Why not? See, suppose I have 4 quadrant, first, second, third, fourth. Okay, say I am asking robot to go somewhere, some coordinate, not robot, anything, plus, which is the coordinate +2, +2. That is in the first quadrant, right? So what is this angle? This angle is, tell me, tan inverse 2 by 2. Tan inverse 1 means 45 degree, right? So if you do if you solve theta i's in terms of tan inverse, sine inverse, cos inverse function, this is wrong. I will give you a big 0. Why? Now you will know. So if now I am asking robot to move -2, -2, that is in third quadrant, what that function will do? Tan inverse function. Tan inverse function will still calculate -2 by -2, and it will give you tan inverse 1, and you can check it, pi by 4, which is wrong, because I have asked robot to move here, -2, -2. Instead, it will move here. So you understand why kinematic solution will not accept anything other than a tan 2 function. And by the way, this function is called a tan 2 function. All my students in their first initial classes, they actually program this is a library function for any language nowadays. But if you have tan inverse function, you can redesign a tan 2 function, which is a must for acceptable inverse kinematic solution. And the reason you know now. So we have kinematics, inverse kinematics. Does it enough? It is not enough to calculate only theta. Why it is not enough? Because you see, these thetas are time function. Okay, so robots are there. Theta is a function of time. This is another theta 2 is also a function of time. So you are merely telling robot to say follow a trajectory corresponding to this point, it can calculate the inverse kinematics, and it will have all the theta values, theta I values by optimization and inverse kinematics, and thereafter optimization, because inverse kinematics will give you actually in this form you will get E 10 2 plus minus blah blah whatever, right, comma plus minus. So when you solve any typical robots inverse kinematics, okay, even if you solve three-link robots inverse kinematics or two-link robots inverse kinematics using matrix form, you will see multiple solution will be there. So first you'll have to solve inverse kinematics, then optimize. Okay, optimization is very easy, that wherever robot currently is, it has to select those theta for which it has to move less. That's it. And after that, what? Robot will move? No, robot will not be able to move, because this the model is very incomplete model. First of all, in this model we have link L1, L2, but we have not told robot. Say we have some kind of matrix and theta. Okay, this is what it is. We have not told at what velocity robot should move on this trajectory. It can move very slowly. Robot is moving like this in a particular trajectory. And robot can also follow the same trajectory with a very high speed. So unless the planner is instructing robot to do that, it will not be able to move, unfortunately. Okay. So what to do? We'll have to, let me have some, yeah. So we'll have to solve. I believe I do not have much time, right? Although the organizer, please tell me when I need to stop, I will stop. But I need to tell my students about this.
Sure, actually, sir, the allotted time is till 10:45, but we can extend more 10 minutes, sir. 10 to 15
okay,
minutes.
So yeah, I need to tell about this concept of Jacobian. Why inverse kinematic solution is not enough to control a robot, one student must know. So you see, I already had with a simple example cos theta 1, I am writing C1, okay, plus L2 cos theta 1 plus theta 2. We had this, okay, in our sin theta 1 plus L2 sin theta 1 plus theta 2. So by inverse kinematic solution, you have got theta, but you have not got theta 1 dot. Means I need to specify robot with what velocity it should move. So I need to calculate this. Okay, just by differentiating, you will be able to calculate very easily. Okay, it's very simple. Okay, then theta 1 dot plus theta 2 dot. Then if you just try to do this, okay, so plus L2 cos. So if I now write in this form, theta 1 dot, theta 2 dot, okay. So now we can fill out this theta 1 dot is there. So this and this will be my first element. This is for you, okay. So you'll have to do that. So this is very interesting. This is called manipulator Jacobian matrix, okay. Here it is 2 cross 2 matrix, okay. Now for 6-ring robot, it will be 6 cross 6 matrix. For my robot, which I have shown, the Baxter, it is redundant robot, okay. So we have 7 joints and 6 degrees of freedom, okay. So that's another problem which we are solving in a different way, how to make a relation between the motion, you see. So this is another problem. If I write in vector form, I'm sorry. So from very first principle, I am writing, right, with 12 class calculus. So I have this relation now. I have this relation now for 2-link manipulator, and this is called manipulator Jacobian matrix. If you see the structure of the Jacobian matrix, it is configuration dependent. Means The moment robot structure is robot in motion, this matrix need to be upgraded. It is configuration dependent matrix. It's not fixed. So if I try to now, so additionally, what I will have to tell now robot, go here with this velocity. Otherwise, robot will not, whimsically it can select any velocity. Okay. So if you tell robot, define this velocity, the Cartesian space velocity, robot need to solve at his joint space, because the robot has only to move his joint, and you will have to do this, okay, inversion of this Jacobian matrix. And wherever matrix inversion is there, it's the problematic, as you know. Why it is problematic? Because first of all, it has computational complexity, big O n cube. N is the number of elements, which is not good. It's computationally not efficient, and robot is a real-time system. Second, this is good. So far, so good that it is a 2x2 matrix. For Puma, it is 6x6 matrix. But for my Vexter robot, which you have seen the demo in the first video, it is having 6x7 Jacobian matrix. So inversion of this is not possible. So what we do? We have to do pseudo inverse by, you see, let me see. Hi, yes. So this is my robot, right? Vexter. We have called it Onukul robot after the great writer Satyajit Ray's first movie, which he visualized what robot should be and what is trying to do that. So this is what inverse, that pseudo inverse we will have to calculate the Jacobian matrix. And without Jacobian matrix, robot will not know what is theta dot. And if it is not knowing what theta dot it has to follow, then you cannot implement this kind of control. So the control. So we have now telling you two types of thing, right? One is kinematics, and then kinematics is merely giving information what will be the theta for some defined x. Then Jacobian is telling me what should be theta dot for some defined given this. Okay, so this with this two thing, no, somehow we can control the robot. We are not going for the paucity of time, and believe me, it's so complex. We are not going detail into the dynamics, and nobody is using actually, unfortunately. In the industry, it is so complex, but this is perfect model. As a mechanical engineer, we must know that this is kinematic model, but incomplete model, because there is no mass property. This is more complete, more complicated, and more difficult to implement in real life. But in for teaching student, we spend a lot of time in solving inverse dynamics, forward dynamics. Here it is inertial matrix, Coriolis and centrifugal matrix here. This is actually, you have gravitational matrix, everything in the form of matrix. Okay, coupled form of equation can be derived, and we derive, and I think every faculty derive for their student, but it is, believe me, less utilized in the industry, because when we tell them, oh, very X, they will see our beautiful equations and they are working, and they will be very excited. Oh, it is great. But when they will implement, the one very simple thing. Okay, this is an example which I will tell you again. Sorry, Elon Musk example that he first tried to implement. Okay, implement the this completely. He wanted to robotize hand in eye coordination. He wanted to implement, but miserably it failed because our technology is so far confined. Many great things we are doing in the laboratory only. One of them is actually dynamics. Implementing in the real life is very difficult. But if you know kinematics and if you know Jacobian, you can control, because now you have to guide. You have two commands: go there with such and such velocity. Then robot will be able to synthesis through his computer what will be the theta, what will be the theta dot, and then at the execution level control, we have PD, PID, all kind of, those are very standard now, but they are another domain called execution level control. Okay, so using those execution level control, we can really make a robot move. Okay, so it's not, nobody can do the justice with 1.5 hours to tell you about the control complexity, but you must understand that this is what planner is doing. What planner is doing? Planner is actually synthesizing theta d, desired theta d dot, and if you have theta d dot, using some computation manipulation, I can always have theta d double dot. That is my desired joint value, desired joint velocity, desired joint acceleration. Then using the proportional derivative type of control. This is incidentally, by the way, this is computed torque control or model-based control, which is extremely popular in the industry because of its simplicity. So once these values are given, who is giving these values? My computer. Because computer can already do this, only pass those kind of data. Okay. Now with that data, who will be executing it? There are execution level controller, which I would like to tell you that say, this is my computer. Okay. And there is an interface. And there are microprocessors. Okay, every joint in case of Puma or any industrial robot has a number of, as many joints are there, that many microprocessors will be there. Okay, so if you have 6 joints, 6 microprocessor, because those are the execution level controller. This computer will pass message and then they will actually control the joint. They will control the joint means they will control the motors. And here PD, PID, all kind of control strategy are implemented. Okay, so this is actually the control structure from an implementation point of view. Every joint has this kind of structure. And then what is happening? So every joint, how they are actually, so message is passed from computer. And what is the role of interface? You see, in an orchestra, perhaps you have seen one guy who comes in the stage and then after going down, after greetings, he turn around and he control all the members of the orchestra. So interface is doing that job. Just that will be very clearly understood by this. You see, now you are getting theta d. Then I am drawing what is happening to the microprocessor level, right? Here what is happening. So microprocessor is getting some value, desired value, and then that is a data which cannot move anything. So I will have to transfer that digital signal into analog one, and then they'll be mostly very feeble. I'm talking about your armature current control type of motor control. Motor can be controlled by other means as well, and will give you some actual value. And there has to have some sensor which is known as encoder in case of robot. So as you know, so what is microprocessor? You know, microprocessor is a computing machine where you have 3 basic elements: register, that is the memory, control, and CPU actually. Okay, this is a processor, consists of memory. So lots of memories are there. So it is getting some value theta d from the planner. Okay, and it is immediately through this sensor and keeping it in one of the registers. If it is a 4-bit register, it will keep there with an address. Then another value will come, it will read, okay, boss is telling me to move that particular joint, okay, by this amount. Now, where my particular joint is, so this is at every joint level, this loop is running. So what is my particular joint at that time, at this present time. So encoder will give, and it will keep that in another register, right? And we can write simple program at the assembly level to compare the content of the two registers. If they are same, no action has to be taken. Means what boss is telling, my robot joint is already there. But if there is a difference, there will be error. Okay, so it's an error-driven feedback control loop, error-driven system. So error actually has to be in digital form, has to be converted to analog form. Then okay, corresponding to the error, I will have to amplify the current, and then I will have to control the torque of the motor till new A is coming, theta A is coming, and this will continue in a loop. Normally 0.1 millisecond it takes, and somehow 200 epoch or loop it takes for an industrial robot to correct what boss is told. What boss is told, this is the implementation the microprocessor will do at every joint level. I believe this is understandable. And the interface is doing excellent job. What it is doing, stream of data is coming from here, okay, at any instant. The interface is telling, and the interface is distributing that data to all the addressed joint microprocessors. And you see, maybe this joint will move less, this joint will move more, and with more inertia, so it will take more time. Interface job is to just take see that okay, so every joint level microprocessor has to give a signal. Okay, I am done, boss, I am done, I am done, I am done. So all the joints, when they will give that I am done, then only interface will assure the boss that okay, you can now send me the next stream of data. And that's the way, in a very good hand setting, interface is doing between computer and the low level or the execution level controller, and making robot move. So that's the story I wanted to tell you. And these are the, now, some basic research about IIIT, what we are doing. Okay, they are, you see, based on, you see, this is a human-robot interaction. This kinematics and control is actually a small part of what we are doing. Okay, so using gesture, you can actually command the humanoid robot. And this kind of, by the way, this kind of robot are envisioned to be the future robots which people will have in their house. Okay, we believe one day it will be there. So we are trying to communicate with the robot using our universal devices, that is gesture, speech. Okay, let me see. So can you hear the sound? No?
No, sir, sound is not audible.
Okay. Okay, sound is not audible. So basically this is a robot, and then it is being instructed. It has shown some device, and it understands that, okay, it is a ball, so I will have to be ready to play the ball. So that ready, play the ball, you can design anything. That's a just story. But the thing is that communication using gesture and speech, and both, is very humanoid way which we are trying to do, because that's I believe the future, because robot, if it is working in your home, you are not expected to be either mechanical engineer or a computer engineer to operate it, right? So people should be operating it with the way we operate our mobile phone, using speech, gesture, and all kind of thing, right? So these are some of the wonderful research we are doing. You can visit my YouTube channel to see some of them. All of them are there. Okay. So these are for the paucity of time. I am concluding here with a note that beyond kinematics and control, human-robot interaction is the focus, tomorrow's focus. So while as a mechanical engineer, you must learn kinematics and control, they are actually getting very standardized in the industrial sense, because we did a lot of research in dynamics, control, and very small fraction, as usual, has been taken by the industry, because many simple things are coming into the picture. But there is no simpler thing than what I described here. That is inverse kinematics, forward kinematics, Jacobian, and manipulator control. So with this cool video, I will just end. This is a Sophia robot, you see. And recently I was surprised that ISA Bangalore is having ASA robot. And I thought that they have developed their ASA robot, but it turns out that they have a collaboration with Sophia robot. Sophia robot's infrastructure they are using for speech and gesture recognition, which we are also doing a lot of works in that area. So this is Sophia. It's known to you that Sophia is the first humanoid robot got the citizenship from Saudi Arabia. Okay, and it can communicate in a to some extent to a cognitive level. So what this is a creator of the Sophia robot, a team of scientists created. Okay, and inside it has a structure. That's fine, but the main issue here is some problem need to be solved in the cognitive level. That how it can understand the language, how it can understand your gesture correctly, and how using those gesture you can communicate with the robot. And then only in our household, which is another potential area, because industrial robots are there in the industry in the range of millions. They are doing their job. And as I told you, they are using very little of the technology which we have developed today. Mostly you will be surprised they are working on teach-pendant mode because that's simple and that solves their problem. But we have to be ready to solve many problems which will be associated when robots enter to our house. And that's where the technology will skyrocket, I believe, because demand will be large. Every people, just like personal computer or laptop or a mobile phone, they will have personal robot, and many problems for that. We as engineer getting together, mechanical control, computer science people, everybody should be together to develop technology for this thing to happen. Thank you for your attention. I stop here. If you have any question, I'll be happy to answer.
Thank you, sir, for broadening our knowledge on importance of robotics in the field of mechanical engineering, for helping us develop a deeper understanding and clear articulation of the topic. Hereby, we conclude our presentation. Now, sir will answer any of your queries and questions. Please raise your hand so we can unmute you.
Guys, kindly raise your hand, those who have a question or want to interact with the sir. Students?
So if no question, then faculty can also ask some queries or give some suggestion.
Sure, sir. Actually, sir, we do have a ARC, that is Agile Robotic Club, and they were too excited to listen from you.
Okay. Please, is it a question?
Actually, I was.
Hello?
No, sir. Actually, I was suggesting that there was a student who actually was willing to attend, and they have understood, and they should have some questions basically. As sure. I am waiting for. I'm just want to them to know. Guys, any question?
Okay, so
no issues, sir. No issues. I guess it must be they have understood everything. I guess we have a one
or maybe the other way around. Okay.
Anyway, yeah. So one question we have, sir. Jayesh, you can unmute
hello, sir.
You can talk. Yes.
Go ahead.
Sir, I want to know that like Sophia robot, are there any other projects like developing a humanoid?
Yes, actually, we have a number of humanoid robots. This now is one of them, and we have Hope 2 humanoid open architecture platform. And also we have a robot which our student developed, which is called SMART, Social Mobile Autonomous Navigation Test Bed. And all the videos, actually how they work, what they do, is available in my YouTube channel. You can just visit. And we have also my course in robotics. So you can also, if you have any queries or understanding, if you want, so you can visit them. So those are the humanoid robots. Now at present we are working on Onukul robot, which is also a humanoid robot. It's cobot actually. This is called cobot. Earlier the thing was the robot has to work in an autonomous way in the industry, and that's why we are putting them in the cage, because they were very unsafe. They are in, if somebody is coming in the working envelope, within the working envelope, they may hit. Okay. And those robots, as I told you, because of the issues with the dynamics, robots themselves were very heavy, but they could carry only a meager load, 500 gram, 600 gram. Okay, a robot which weigh say 60 kilo or 70 kilo. Isn't it very bad? But technology today only permits that. Why it is so? Again, mechanical engineer can understand, computer engineer can understand, because the moment with heavy load robot is moving, okay, there are inertial torque, which is experienced by the actuator, and it's very difficult to model them. Okay, it's very nonlinear forces which varies with the acceleration. Okay, so those are the issues which confined so-called industrial robot in the cage or a zone where when robot works, human cannot go. But the research in the area of robotics, which we are doing and around the world people are doing, robotics means robot and human will coexist. Our Baxter robot will not hit anybody. If I go there, I can just make a handshake, I can just pull along with his arm, and it will work in a friendly fashion with me. So the idea of implementation in the soft floor robotics is undergoing a sea change. Now people are trying to implement cobot. They are basically, you can interact with humanoid robot, but having arm only. You can see that Baxter robot, which I have shown you the video. So they actually can do the job which you cannot, but as a friend of you. So they are merely supposed to work as a tool of a skilled worker rather than replacing the skilled worker. And that's actually improving the quality of the product and quantity of the product as well. So that's the present scenario of humanoid robot, also percolating down to the industry. That one project we have, we are trying to understand the grasping, intelligent grasping mechanism. You see, we can grip the object, any object, very conveniently, right? But a kid cannot. You see, their parents are reluctant to give them something made up of glass or something, because their skill of grasping is very poor. But over the year, the same kid learns how to grasp objects in a skillful way. But in case of robot, we only plan, and that is failing. Only plan-based robot, which as a mechanical engineer we did earlier, is not able to do the job which industry wants. Up to a certain level, it did. So we'll have to impart intelligence, learning-based intelligence, experience-based intelligence. You see, same kid, when it grows up, it can handle a glass of water or any object very skillfully. Okay, so learning is this process, and the mechanism of that we are trying to understand thanks to deep learning and machine intelligence. Okay, so those are the tools which are making our robot to learn from experience. That's the project which are involved my team, myself, very intensively. Okay, at present. Yeah, I see another hand.
Okay, sir. Thank you, sir.
Okay.
I guess next we have Anish. Anish?
Yes, sir.
Yeah.
Yes. So my question is, can you recommend any like affordable hardware and software for doing inverse kinematics and forward kinematics for a mobile robot, like robot which moves.
Okay, yeah. For paucity of time, I did not tell you about the kinematics and control of mobile robot. Although they are relatively easy, but same principles we can follow. Say you have a wheel mobile robot you have designed in your lab. Okay, so first you need to understand that the issues of kinematics there. If your wheel move, then how much your body will move. Okay, so moving the wheel with the help of motor again, you are getting some trajectory of the robot body which is resting on the wheel is your forward kinematics. But if I specify the body has to follow a certain trajectory, avoiding collision and all kind of thing, then what will be my wheel speed and direction to accomplish that is my inverse kinematic solution. And in case of manipulating robot, you know that Denovet-Hartenberg principle or notation is used. And in case of mobile robot, Seth-Wicker principle are used. Seth-Wicker, Sethwicker, Seth-Wicker principles or notations are used. But the issue with mobile robot is not intense in terms of inverse kinematics and forward kinematics because making robot to follow a particular trajectory avoiding obstacle is extremely difficult. So what we do, we allow robot to move somehow some trajectory which is collision free. And we as human also do the same thing. You can do an experiment at your home. You see, if your mom is calling you for lunch, so if you think that I will follow a particular trajectory and I will go from my reading study room to kitchen following that trajectory, you will have to be extremely careful and it will take a lot of time. And if you do not allow yourself to deviate from the trajectory, it will be a very hard job. But we don't do that. Every time you are going from your study room to your kitchen or the dining room, you follow different trajectory. But none of them are unsafe. And that's the strategy. That's why algorithmic strategy we follow in case of wheel mobile robot. So the mechanics, that's forward kinematics, inverse kinematics, not stringently required in fact. Instead, we can do slum implementation, simultaneous localization and moving, right? Localization and mapping. So if you have a map that's where to go, if you know where you are, you can plan a path. That path need not be a stringent trajectory. So that's why those problems which you can solve, but are not very in demand. Rather, you should try to solve SLAM, simultaneous localization and mapping. Okay, indoor SLAM, outdoor SLAM. So a lot of people who are working with wheel mobile robot or mobile robot are engaged in this kind of activities because they make sense. Did I answer your question?
Actually, I also wanted to know. Also wanted to know the hardware that is used in this. Like right now, you showed a video about humanoid and also a robotic arm. So, what hardware it runs on? Like I understand we can also use SLAM, but like I'm interested in knowing the hardware.
Okay, hardware, wheel mobile robot, you can just, for example, very low cost hardware is Locobot. Okay, again, Locobot you can also design in your own lab. They're extremely simple, but hard thing is to design the controller and the computation part. But those days are gone where you will develop a robot. Okay, for your understanding, you should, okay, in a club, you should make your hand dirty to know how to program your microprocessor and how to collect data from the sensor. But you will have to also go to a next level where the main challenge is to design the interface, because today's all robot, unlike 90s and 2000s, right, where early 2000, where industrial robot manufacturer, they wanted to actually hide their language. That's why assembly level language, there are plenty. Val, Sigla, Autopass, and if you write Val code other than Puma, the Kuka robot will not understand. You need to know Kuka's language. So all this bullshit has gone now. Okay, thanks to a great team in Carnegie Mellon and some German scientists. So in 2010, 11, 12, during that time, they came up with an idea called Robot Operating System, or ROS. So that is actually the game changer. Now, if you can learn ROS, Robot Operating System, where all the libraries are there, and your robot has to integrate with ROS. If it is not, nobody will buy your robot today. Okay, so you can program your robot using either C, C++, or Java, or Python. Okay, so that you can do no more Val, Autopass, Sigla. We have functions now. Okay, and those any robot you develop has to be ROS integrated, and it is not that difficult. First of all, you need to know about ROS, Robot Operating System, ROS, and try to make your even small robot with at some microcontroller you can buy, and then you'll have to design the interface though. Okay, and you have a computer or laptop, you can control the motors. Okay, those things you can do, but further challenge will be how to develop the driver so that your robot should be acceptable, will be accepting the command from ROS, Robot Operating System, which is state of the art now.
Okay, sir.
Yeah.
Nandi, sir, we'll take a last question from Shoaib sir, and then we'll Shoaib sir.
Yes, sir.
Yeah,
Am I audible?
Yes.
Yes. You are audible. Perfectly.
So my question is like a bit vague, I would say. I wanted to know, like, when you said that we are now working on robotics, which is
Yes. Human robot collaborative environment. Yeah.
Yes.
Go ahead.
So, this is now the trend which is like in the industry, I would say then.
It is now the?
It is. I would say that this is now in trend in the industry or in the research field, right?
Yeah.
So, is there anything like work going on about the movement? I mean, the degrees of freedom that you were talking in the initial slide, like when you were showing about the robotic arm. So you said there is only 1 degree of freedom which is available, and because of that,
1 degree of freedom per joint. 1 degree of freedom per joint. Yeah.
Yes. So, like now, are we working on this, like to move to increase the degrees of freedom for per joint, or is there like a stop put to it?
Very good question. So very good question. I will try to answer it. You see, today with the availability of huge computation power, the robot are not constrained to have only 6 degrees of freedom. We can have dexterity. Means we can add more joints, but joints will give you dexterity, isn't it? Means dexterity means you can easily reach somewhere with by manipulating minimum number of joints. By manipulating minimum number of joints, that is the dexterity. Okay. So our fingers is dexterous. Okay. So that cannot be achieved unless you give redundant degrees of freedom. Means degrees of freedom which is additional to the required one. Okay. So today's cobots have additional degrees of freedom, and those additional degrees of freedom makes our kinematics more complicated. As I have just touched upon, our Baxter has 7 degrees of freedom, and it's not following well. Somehow it tries to follow that Craig's Piper's recommendation, but even if it is not following, that's not an issue. I can develop kinematics and that Jacobian for this kind of robot with additional they will add additional complexity. For example, in case of Baxter, I have to solve the pseudo inverse, to have a mapping between Cartesian space velocity and joint space velocity. Because you will define, or the user will define, Cartesian space velocity. So robot need to know at the joint space what does it mean, and for that it need to solve the pseudo inverse. That's put additional complexity, but it is doable today because we have computers and all kind of Python libraries, so it is doable. Okay, so although additional complexities are there, we are still want this kind of redundant